Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about epidemic models. So what do you mean by epidemic? So an epidemic is defined as an unexpected increase in the number of disease cases in a specific geographical area, that is an unusually large short-term disease outbreak. For example, you have seen this COVID-19. So that is an epidemic. However, we generally use this word pandemic. So the difference between this pandemic is that the outbreak will be called a pandemic when the disease growth is exponential. That means it is very, very high, very, very fast. So as we have seen in the case of COVID-19, the infectious rate is very, very high. It was just catching up exponentially. So that's why we use the word pandemic before this COVID-19. There is another word which we use which is called endemic. So if this disease is consistently present but limited to a particular region. For example, we can take this malaria, we can take cholera, we can take sleeping sickness. So these are endemic disease where in many parts of the world. So the difference between this pandemic and endemic is that this pandemic the growth will be exponential, and in endemic it is present consistently but limited to a particular region. So how do you model this kind of endemic diseases? So and what is the purpose of this endemic models? So basically endemic models, they are primarily designed to explain and predict the spread of this infectious disease, whatever the disease may be. And the little history is that the first model, not the first, the first compartmental model, it was proposed by W.H. Hammer in 1906, and he proposed the model where the spread of infection, it depends on the number of susceptible individuals. So what do you mean by susceptible? It is that the persons who are vulnerable to the disease. So those are called susceptible individuals. And the number of infective individuals, that is the person who have already got the disease and they are called the infective individuals. So by compartmental model we mean that there are classes, like this class is called the susceptible class, this class is called the infected class. And he suggested this law of mass action for the rate of new infections, and this idea is the basic of this compartmental models. So we will be looking up into some compartmental models. The origin of such models is in the early 20th century. The names famous for this model are Ross in 1916, Ross and Hudson in 1917, Carmack and McKendrick in 1927, Kendall in 1956. So let's start with a very simple kind of model, that is the susceptible and infected model. But before that, let's have a look at this particular graphics. The left hand panel which you see here, the population is getting infected, and the right hand side it gives you the graph that how this population is behaving. So it will start with some black spots like this. So these are the susceptible one and they are getting infected very fast, which is the red one. And here you can see that the susceptible is coming down, the infectious is growing up, and then this green one is the recovered one, and this is the total population that has been infected. So this is what the mathematical model gives you, and the goal of the epidemiologists, that is the persons who study this epidemics, is to first understand this cause of the disease, then to predict its course, and finally to develop a way of controlling those diseases. So we start with our first model, that is the susceptible and infectious model. So, the susceptible ones are the ones who are vulnerable to the disease, and the infected one, the one who has been infected. So, if I connect these two compartments by some beta, so it means that when the susceptible is coming in contact with the when the infected person is coming in contact with the susceptible, they get infected. So, if I say A to be the S to be the number of susceptible and I number of infected, and beta is the rate at which this is happening, a person gets infected. The model will look very simple. This is ds dt and this is di dt. So, ds dt, when it comes in contact with a infected person, the person gets infected at a rate beta, and from the susceptible class it moves to the infected class. So, a minus sign here and it moves to the infected class. So, plus beta Si. So, one more time, this is the rate of change of the susceptible, this is the rate of change of the infected person. So, when the infected person is coming in contact with the susceptible person who are vulnerable to the disease, they are getting infected at a rate beta and then moving to the next class, which is the infected class. And since they are moving, this is the negative sign and the whole thing comes here, this is the positive sign. Now, you have some initial condition, say initial values. Say at time t equal to 0, let there be n susceptibles, and at time t equal to 0, there is only one infected. So, total population becomes n plus 1. We want to see what happens to the whole population over large time. So, you can see from here, if I name it as 1 and name it as 2, if I add 1 and 2, I get ds dt plus di dt, and that is equal to 0. This 2 gives you 0, which implies ddt of s plus I equal to 0, which implies st plus it equal to constant. So, you have st plus it equal to constant. Your initial condition S0 was n, I0 was 1. You substitute it here, you get S0 plus I0 equal to constant, and the value is n plus 1. So, that is the value of your constant. So, you get St plus It equal to n plus 1. Now, you have the equation ds dt is equal to minus beta Si and di dt is equal to beta Si. Now, I will be solving this differential equation using this relation. So, if I write ds dt equal to minus beta times Si. So, what I will do is minus beta times s, I is replaced from here. So, I is n plus 1 minus s. So, this I will put here n plus 1 minus s. This is ds dt. Separation of variables will give me ds by s n plus 1 minus s equal to minus beta dt. Now, the easy way of solving this is, it's a partial fraction. You just write 1 by n plus 1 minus s, 1 by s. Now, you can see if I simplify this, your s cancels provided there is a plus sign. If this has been plus, I would have put a minus sign so that the s cancels and you are left with a constant. So, if I simplify this, it is s plus n plus 1 minus s, s cancels. In the numerator, you have n plus 1. So, I divide by n plus 1 because there is no n plus 1 in this numerator. So, this whole thing is just written in this form. If you simplify this, you are going to get back this, and this is minus beta dt. So, cross multiplication will give me 1 by n plus 1 minus s plus 1 by s ds is equal to minus n plus 1 beta dt, and you integrate both sides. If you integrate this, this is ln n plus 1 minus s with a negative sign because here it is negative, plus ln s. So, ln is log to the base e. This is minus n plus 1 into beta t plus constant. So, at time t equal to 0, your s 0 equal to n, and this gives minus ln n plus 1 minus n plus ln n equal to 0 plus constant, and this implies constant is equal to ln n because this gives you log 1, which is 0. Now, I substitute it here and I get this equal to minus ln n plus 1 minus s plus ln s equal to minus n plus 1 into beta t plus ln n. So, you take all the logs to one side and you get ln n plus 1 minus s minus ln s plus ln n equal to n plus 1 into beta t. So, I take this to this side and all of this to this side. Then this is n plus 1 minus n divided by s multiplied by n equal to n plus 1 into beta t. So, n plus 1 minus s into n divided by s equal to e to the power n plus 1 into beta t. So, just rewrite it, n plus 1 minus s divided by s equal to e to the power beta n plus 1 into t. You just divide. So, n into n plus 1 divided by s minus 1 equal to minus n equal to e to the power n plus 1 into beta t. So, I am just solving for this s. You take this to this side, n plus 1 into n divided by s equal to n plus e to the power n plus 1 beta t. And just cross multiply, your st is n into n plus 1 divided by n plus e to the power n plus 1 beta t. And since we have this relation it st plus it equal to n plus 1, I do not have to solve this it again from the other differential equation. All I have to do, it equal to n plus 1 minus st. So, the it is equal to n plus 1 minus st, which is n into n plus 1 divided by n plus e to the power n plus 1 into beta t. So, I can take n plus 1 common. 1 minus n by n plus e to the power n plus 1 into beta t. If I simplify, I will get n plus e to the power n plus 1 beta t minus n divided by n plus e to the power n plus 1 beta t. This n cancels, and I will get IT equal to n plus 1 times e to the power n plus 1 beta t divided by n plus e to the power n plus 1 beta t. So, just divide by this particular quantity, both numerator and denominator, and you will be getting n plus 1 divided by n e to the power minus n plus 1 beta t plus 1. Or you can just take this common, and then this particular term and this particular term will cancel, and you are left with this st. And I just rewrite this st, which is n into n plus 1 divided by n plus e to the power n plus 1 beta t. Now, let us see what happens as your t becomes large. So, as t becomes large, your IT goes to, so as t becomes large, e to the power minus this goes to 0 and the denominator is 1. So, you are left with n plus 1 by 1, which is equal to n plus 1. And your st, as t becomes large, this is exponentially growing. So, this goes to infinite, and the denominator goes to infinite, and hence it goes to 0. So, what is happening is, as time increases, all the susceptible, initially there was n susceptible and only 1 infected, but as time becomes large, all the persons of the population gets infected, because the total population is n plus 1, and your susceptible goes to 0. So, as time increases, all the susceptible persons will become infected. So, this is just a basic model of the susceptible and the infected. Let us see the numerical solution of this particular model, where I will be using this Microsoft Excel. So, I already have it here. So, this is the equation, ds dt is minus beta si, dy dt is beta si. So, initially I am choosing the value of n to be 2000 and only 1 infected, and the value of beta, it is not 0, it is 0.001. This is your initial value for the susceptible, the initial value for infected. So, let us put the time at 0, this value is 2000 and this value is 1. So, this will be equal to this plus 1, and let me drag it say to 83 of the values, and this we use as usual the Euler's method to solve this system of differential equation. The formulas are given here. So, this is equal to this S0 plus H times, which is again a constant. So, I put dollars times minus beta, which is this, again dollar and enter. So you get this value, and this is equal to I0 plus again the value of h, which is constant, multiplied by beta, again a constant, multiplied by s into I. Sorry, here it is just the constant, forgot to multiply by s into I. Yeah. So now let's drag these two values. Okay. Now we plot this. You highlight by pressing the shift button and to the how many values we have up to 83. Go to insert, choose this scattered diagram and this graph. So you get this curve. I don't like the grid, so you may keep the grid. If you want to remove, click the plus sign and uncheck this grid lines. So you can see the grid lines are gone. I want the axis, so this is the axis title and the chart title. So the chart title is SI model, the axis title is time, and to this. So here you don't have to bother the way it is written. If you just click the cursor, it will automatically will be in this vertical thing, and you just press backspace, it will remove. So this is population, and ultimately this series, you go to this chart design, select data, here it will come series 1, edit. So series 1 is susceptibles, and series 2 edit is the infect. And okay. So this is my curve. From 2000 all the susceptible goes to 0 and this reaches the value 2000. Now let's go back to our lectures. Let's quickly see the numerical curve. So we plotted this curve using this Microsoft Excel, where I have taken the initial value as 2000 for the susceptibles, only one infected. These are the parameter values where your beta is 0.001, initial values, the Euler's method for solving, and you get this curve, which is the susceptible and this is the infected, which shows that as time goes becomes large. So with time all the susceptible will be infected. This susceptible comes to 0 and the infected reaches the value 2001. So summing up, we have started with a SI model, which is the susceptible and infected model. We form the model with the help of differential equations, we solve them, and we see the dynamics of the model as T becomes large. In my next lecture, we will be starting with a SIS model, which is again a two compartmental model, but here we have a susceptible, we have an infected, and from the infected class some is going again to the susceptible class. So, we will be seeing that how the dynamics changes in an SIS model and how it differs from the SI model. Till then, bye bye.